Now, we can use the integral formula from my previous clip in order to calculate the area contained by a polar curve. I also want to talk about using integrals to calculate the arc length of polar curves. So here I've graphed this sort of diagonal facing parabola. Its equation is r equals 2 on 1 minus the cosine of the quantity theta plus 1. In order to calculate the arc length, I'm going to perform a similar integral to what we've seen before. We've done arc lengths in rectangular coordinates. We've also done arc lengths for parametric curves. So if you can imagine that same argument that I've made before about approximating the integral, or excuse me, I'm jumping ahead of myself, approximating the arc length by a bunch of line segments, and then using an integral to go from my approximation to the actual value. A similar idea is going to play out here. Now, the formula that we want to use is slightly different. This is an integral that we will compute with respect to the variable theta. So my integral formula will come with a d theta. And I'm picking two different values of theta to integrate between, let's say a and b. And I need to describe what my integrand is going to be. Now, we've seen these arc length formulas before, where I'm taking a square root because I'm setting myself up to use the Pythagorean theorem. And what do I need here? I'm freehanding it because I need to do some fractions. I'm going to have the square of my x derivative plus the square of my y derivative. And this will look a little bit different because we're in polar coordinates, working with a polar curve. So I'll have dx on d theta all squared. This is my derivative in x with respect to the variable theta. And then I'll add that to dy on d theta all squared. My derivative of y with respect to the independent variable theta. Now, this looks workable. I have to remember that my x is equal to r times the cosine of theta. And my y is equal to r times the sine of theta. And bear in mind that r itself is a function of theta. So when I calculate these derivatives, I would need to use the product rule. Now, I'm going to spare you the details for right now. We can talk about it in person if you really want to see it. But I'm going to skip ahead to an easier formula. There's some trig identities involved in simplifying this. But this is the arc length formula for polar coordinates. So again, we have an integral. I'll choose my two values of theta in just a minute here. And what I'm going to integrate is the square root. I'll have, excuse me, I'll have two things squared here. And what is it going to be? I'll have r squared plus r prime squared. All of this d theta.